Greetings grade 12s and welcome to Ubuntu Academy, lessons that empower. Today we are going to be looking at one of the exciting topics in mechanics, and that is work, energy and power. This is one of the topics that will be assessed on your paper 1 examinations. That would be in the June exams together with the prelim exams and the final examinations. The topic that is usually assessed on question 5. Of course, changes might happen depending on your examinations. So before we go into details, I want us to first look at the examination guideline. Remember, we use the 2021 exam guideline for physical sciences. Let's look at page 10 of your exam guideline, and this is what you're going to come across. If you look at your page 10, you'll see the topic work, energy and power, and of course it has to be read in conjunction with the CAPS document. Now, the first thing under work is the definition of the concept of work, okay? And today's lesson is going to be precisely about that. Now, work done, as you can see there, you are expected to define work done on an object by a constant force as F delta X cos theta, and that is exactly the definition of work done. Simple as that, okay? Now let's go to breaking it down. Work done on an object is defined and calculated as you saw in the exam guideline. The work done is actually defined as the F delta X cos theta. Now let us get into all those elements that you see appearing in your formula there for work done as per definition and calculation. The W that you see there stands for the work done, and it's measured in joules, just like energy, okay? F, of course, as expected, is the magnitude of the force acting on the object. Now, one of the most important things that you have to consider there is that here we are only dealing with the magnitude of the force. We don't consider the direction of the force, so that is not important for the calculations here. That will be taken care of. Okay, delta X is the magnitude of the displacement of the object. Now, this is an object that is going to move when a force acts on it. So when a force acts on an object and causes it to move, we can calculate the work done by the force in moving that particular object by using that formula. And also we are going to consider the cos theta there. As you can see, there's a cos theta there. The theta is the angle between the force and the displacement. It is very important that learners understand, especially theta, what angle exactly that needs to be considered there. This is to say, if you have a force acting on an object and the object moves to the right, let's say this would be your delta X, the object moved to the right. Now, the angle here, theta, is the angle between the delta X and the force. Therefore, when you do your calculation for work done, the angle theta there will be the same as that angle there, because it's the angle that is between the force and the displacement. All right, now let us move forward and see, when using this particular formula, there's a few things that you need to consider. The first thing is that for the force applied, or the force that is doing work on the object, you only consider the magnitude of the force. Again, it's something that I mentioned in the previous slide. We only consider the magnitude of the object. We don't worry about the direction, which means there is no need for us to put negative signs there. So there will be no negative substitutions in the formula for work done. W is equals to W is equals to F delta X cos theta. There is no substitution of a negative value there, because we are only considering the magnitude of the force. The same thing is applicable to the displacement, which is the distance that would have been traveled by the object after the force has acted on it. So you only consider the magnitude of the displacement, again, regardless of where the object has moved to, whether to the right or to the left. The value that you substitute in the formula there must be only the magnitude, and again there will be no need for a negative sign, right? And then for theta, now the angle between the force, again remember theta is the angle between the force and the displacement. This is the angle between F and delta X. Okay, and both these variables are in the calculation of work done. When you are doing the calculations and the two are in the same direction, your theta will be 0. And this is to say that forces, or let's say vectors that are in the same direction, are separated by no angle. There's no angle separating two vectors that are going in the same direction. Okay, if you have parallel lines, the angle between the parallel lines is 0. Hence, when the displacement and the force are in the same direction, you are going to use theta as 0. The value for theta will be 0. Okay, now what happens when the two are in opposite directions? So if the force is to the left and the displacement, for instance, is to the right, it means the two are in opposite directions, and in that situation your theta is going to be 180 degrees. And that makes sense because if you think about it, if you have this force going to the right this side, but the displacement is to the left, the angle between these two lines, let's say this is delta x, the angle between these two lines starts from here all the way to that side, and that will be your 180 degrees. Okay, that's why we use 180 degrees if delta x and f are in opposite directions. All right, so those are the three things that I need you to consider when you are using the formula f delta x cos theta, which is the formula for work done. All right, here is a worked example. Let us quickly go through it. Here you have a force of 50 newtons. You've been given the magnitude of the force. It's moving to the right. That's the direction of the force. Is applied to an object on a frictionless surface, which means there is no friction, and it causes the object to move 3,5 meters to the right. If that is the case, then calculate the work done by the force. Remember the formula that we learned in the previous slide. It says the work done on an object is equals to the force that is doing the work multiplied by delta x multiplied by cos theta. Now let us check. We do have the force, it's 50 newtons and it's going to the right, and delta x is 3,5, as we can also see in the diagram there. So our substitution will be 50 for the force multiplied by that will be 50 multiplied by 3,5 multiplied by cos. Now let's think about this for theta. For theta, the force is to the right. Okay, as we can see, the force is to the right, and your delta x, this object moved from this initial point to that final point there. So the object has moved to the right. Therefore, delta x and f are in the same direction. Okay, in the same direction. What did we say in the previous slide? We said if they are moving to the same direction, the theta that we are going to use there must be 0 degrees. Okay, so because they are going in the same direction. Now let's check the calculator and see what would be the answer there. All right. Now in our calculator, we're then going to say 50 multiplied by 3,5 multiplied by cos 0. Okay, and the answer that we get there is 175. Okay, 175 joules is the answer for the work done by the applied force of 50 newtons to move an object from the left to the right. Okay, that is how we calculate work done on an object by a force. So if a force is applied on an object and the object is moving, and then the work done is calculated by saying the force multiplied by delta x, which is the displacement of the object, multiplied by cos theta, where theta is the angle between the force and delta x. Okay, remember if delta x and the force are in the same direction, we use 0 for theta. If the two are in opposite direction, that would be the force is to the left and delta x is to the right. In that case, we use theta as 180 to show that the two are in opposite directions. All right, now let's move on. If you check your exam guideline, it also requires you to understand or to distinguish between positive and negative work. There are some instances where you're going to calculate and find that your work done is a negative value. You find a negative value. Remember, work done is not a vector, so the negative value in that situation does not necessarily or does not at all represent the direction, because work done is not a vector quantity. It has no direction. It only has magnitude. It's a scalar quantity. So what does the negative sign mean in a situation like that? In essence, the simplest definition of work done is actually the transfer of energy. So when you are doing work on an object, you are transferring energy either from the object to you as the person who's doing work on the object, or you are transferring energy from you to the object. Okay, but remember, as I indicate here, this definition is not acceptable for your assessments. That would be your exams and tests and so on. This is just for me to explain to you what actually happens when you apply, when you do work on an object, or when a force does work on an object. What actually happens is that energy is transferred either from the object, from one object to another, or from the person to the object, or from the object to the person. So just remember, this is not a definition that you can use to define work done. This is just for me to explain the difference between positive work and negative work. All right. So when a force does positive work on an object, what it actually does, if the work done, you've calculated the work done and you get a positive answer, it means the force that is doing work on that object is actually increasing the energy of the object. This means that the energy is transferred to the object. Okay, so if your answer is positive, if you calculate work done and your answer is positive, it means the work done, it means the force has actually increased the energy of the object. Okay, now when the force does negative work, that is to say, if you do your calculation and you find that the work done is actually negative, it means that the energy of the object has decreased. Therefore, the force is actually decreasing the energy of the object. This means the energy is transferred from the object to another object, which is the object that is applying a force which causes the object of question to move. Right. So just to wrap it up, at the bottom, as you can see there, positive work, it means the energy of the object increases. So if you apply a force on an object and the work done is positive, it means you're increasing the energy of the object. Therefore, the object gains some energy. If the work done on an object is negative, it means that the energy of the object is decreasing. Therefore, the object is losing some of its energy. Okay. Now let's move to the last part of today's lesson. The last part, we are going to be focusing on net work, which is what the exam guideline requires us to learn. I'm sure by now we all know what the word net stands for based on previous lessons as well. So when there are multiple forces acting on an object at the same time, we can calculate the net work. Okay, the net work done on the object by all the forces. Of course, we all know when we see the word net, it means that we are going to be adding some of the things together to form one value. So W net in this case represents the work done by the sum of all the forces acting on the object at the same time. So what is actually happening here is that the W net is actually a product, or it comes from the F net, which is the sum of all the forces acting on the object at the same time. Of course, most of the time objects are going to experience more than one force. So if an object is experiencing more than one force, we can calculate W net, because each and every force will be doing work on the object. But remember, not every force will do work on the object. Sometimes you'll find that the force is doing zero work, and that usually happens when the angle between the force applied on the object and the displacement of the object is 90 degrees. We all know that cos 90 degrees, if you calculate cos 90 degrees, if you say cos of 90 degrees, you're going to get 0. If the angle between the force and the displacement is 90 degrees, it means the force that is applied on that object is not doing work on that particular object, and therefore it will not be part of the W net which we are calculating in this case. Okay, right. Now, when calculating W net, there are two ways of doing it. Of course, there might be other ways of doing it, but we're going to look at two ways of doing it. The first one would be to calculate your F net first. You could calculate your F net and then use the F net in calculating W net. Then you'll say W net is equals to F net, which you've calculated, multiply by delta x, multiply by cos theta. Everything else is still the same. Delta x is still the displacement, and theta would be, in this case, theta will be the angle between F net and delta x. Okay, that's one of the ways of calculating W net, would be to first determine F net if you can, and then use it in the formula to W net is equals to F net delta x cos theta. Obviously, F net in that case is the resultant of all the forces acting on the object. Okay, or alternatively, what you could do is to calculate the each and every work that is done by its respective force. So here you would calculate the work done by force 1, the work done by force 2, the work done by force 3, and so on, all the way to the work done by force n for n number of forces. So it happens that an object will experience 3 forces, for instance. It means the W net can be calculated by saying the work done by force 1 plus the work done by force 2 plus the work done by force 3, and so on. All right. So in both methods of calculation are perfectly acceptable, and you should learn both of them, because there are questions in some instances where you need to be able to calculate W net or F net or anything in this particular formula using this method. Okay, so you have to learn both of them, or in some cases you'll have to be able to calculate W net using the work done by force 1, the work done by force 2, and the work done by force 3, depending on the type of question. But you have to learn all the strategies on calculating W net. W net is just the sum of all the works that are done by various forces. It can be calculated in these two different methods. Okay, here is the last worked example before we wrap up today's lesson. Here we have a force of 50 Newton acting at an angle of 30 degrees to the horizontal, and it's applied to an object on a rough surface, causing the object to move 3.5 meters to the right. The magnitude of the frictional force exerted by the surface on the object is 8 newtons. So in this case, you have the applied force and you also have the frictional force. There are two forces acting on this particular object. Of course, there is also the concept or the force of gravity, but I need to also just to remind you here, if you were to draw a free body diagram for this particular object, what it would look like is this. There would be this force. Okay, let's just quickly do this. There would be this force applied here, F, and there'll also be the weight, which is the force of gravity, and there'll also be the frictional force because the object is moving to the right. This will be the kinetic friction because the object is moving. Okay. Also, there will be the normal force because this is an object that is on a surface. The surface will be applying a normal force on the object. Now, look at what is happening. The object is moving to the right. The direction of motion, therefore, delta x is to the right, which means the angle between delta x and the weight is 90 degrees. The angle between the normal and delta x is also 90 degrees, which means the force of gravity together with the normal force are not doing work on the object, because if we do the calculation of work done by normal force or work done by the force of gravity, we are going to find cos 90 as part of the formula, and we know cos 90 degrees is equals to 0. So these two are not going to be considered in the calculation of the net work done because both of them are 0. They are doing 0 work. All right. So when we do our calculation in this case, we are going to we could use one of the two methods. Let us use the W net, this formula here, W net is equals to the work done by the applied force plus the work done by the frictional force. If we do our substitution here, this will be equals to the force applied multiplied by delta x multiplied by cos theta plus the frictional force multiplied by delta x multiplied by cos theta. Now let's look at what is happening in the substitution. In our substitution, what we then get is that the applied force is 50 newtons. Then we're going to say 50 multiplied by 3,5 is the displacement multiplied by cos. Now let's think about theta. Theta is given to us there. The angle between the displacement and the applied force is given to us as 30 degrees. Plus the frictional force is given to us as 8 newtons. That will be plus 8, pardon me, that will be plus 8 multiplied by delta x. Delta x is still 3,5 multiplied by cos. Now think about this. The frictional force always opposes the direction of motion. The motion of the object is to the right. Therefore, the frictional force must be to the left, which means the angle between this frictional force and this here delta x must be 180 degrees because they are in opposite directions. The frictional force would be to the left and the motion of the object or the displacement is to the right. Therefore, this would be cos 180 degrees. Okay, so we then go to the calculator and see what answer we get here. Let's quickly check the calculator and see what would be the answer. Let me put the calculator on this side of the screen so that we can see what we are doing there. Now this would be 50 multiplied by 3,5 multiplied by cos 30, all right, plus okay, I should have done that there, plus 8 multiplied by 3,5 multiplied by cos of 180. Okay, now the answer that we get there is that the net work done on the object is 123.55. so we're going to then say this is equals to 123.55 joules, and that is the net work done. Now the challenge to you now would be to for you to go and try and use the other method that we explained in the previous slide and see whether you get the same answer, which is 123.55. Of course, the decimal places there might be the decimals might differ a little bit because of the rounding off and so on. You could try and find F net first and then use it in the formula. W is equals to W net is equals to F net multiplied by delta x multiplied by cos theta. All right, this is just one of the two strategies that can be applied. So try and do this and see whether you get the same answer there. That is how we calculate work done on an object by a force. We use the formula W is equals to F delta x cos theta, where F is the force that is doing work on the object, delta x is the displacement, the magnitude of the displacement, and theta is the angle between the force and the delta x, which is our displacement. All right, let's try to practice as much as possible. I hope that this introduces you nicely and in a very understanding fashion to the concept of work done. In our next lesson on this topic, we are going to be looking at the work energy theorem. Okay, please try and study it first before you watch the lesson so that you can have a better understanding, and also try to do as many practical examples and also problems as possible. This has been Butu Academy, and I hope that you feel empowered. We meet again when we look at the work energy theorem. Keep on practicing. Thank you.